So now we're going to talk about two colligative properties. And colligative properties are properties that depend on the number of dissolved solute particles, but they do not depend on what kind of solute particles they are. When we add a non-volatile, meaning one that doesn't evaporate easily, when we add a non-volatile solute to a liquid, it extends the temperature range over which that liquid remains a liquid. So we understand that water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. Well, what if we want it to remain a liquid at a lower temperature? We can add a solute that will lower the freezing point and raise the boiling point. It extends the range over which it remains a liquid. So the freezing point goes down, the freezing point is depressed, and the boiling point goes up, boiling point elevation. We don't have to worry about this here, but in the Midwest where I grew up, we had ice on the sidewalks in the winter, and ice is very slippery. And so how do you easily get rid of the ice? You can add salt to the ice. That lowers the freezing point, which is the same as the melting point, and thus the salt will melt the ice. The ice will melt at a lower temperature, so you can get it to melt away. Adding ethylene glycol, that's a non-volatile liquid, to water will raise the boiling point, and it also lowers the freezing point. Salt elevates the boiling point as well, but when you're talking about ice, you don't care. So antifreeze. Yeah, question?
Yeah, like if you get alcoholic beverage, you stick it in the freezer, it takes longer for it to freeze.
Yes. So if you have a margarita or anything that has alcohol in it and you put it in the freezer, you may or may not be able to get it to freeze solid because the alcohol is a solute in the water and causes the freezing point of the water to go down. Yep. Ethylene glycol is a common ingredient in antifreeze. You put that in the radiator of your car. The radiator has liquid in it, water, and that cools your engine. Well, you don't want the water boiling, turning into a gas, because then that's when you get these big clouds of steam coming out of the radiator. It can't do any cooling then when it escapes. So we want the boiling point to be higher, so we add ethylene glycol, and so it can go to a higher temperature without boiling. Again, here we don't have to worry about freezing. In the Midwest, in Minnesota, you do have to worry about your radiator freezing solid, right? When water freezes, it expands, and it's going to break something in there. It's going to wreck your radiator. So you want the freezing point to be lower so that it doesn't freeze. Now, you could put alcohol in there, but alcohol evaporates too easily. So we put ethylene glycol in there. It has the same effect. It causes the freezing point to go down, but it doesn't evaporate out. So when we're looking at these colligative properties, we usually express the concentrations not in molarity, but in this very confusing unit, molality. If I was designing this, I would not do it this way. But it is what it is, and that's what everybody does, so we have to figure it out. Molality is very similar to molarity, right? It's one letter difference in the word. So on an exam, if you see something that says molality, do not assume that that's a typo. It's not a typo. Molality and molarity are different. And it's abbreviated with a lowercase italicized m. Like that wouldn't be mixed up for a meter. Well, we're going to keep this molality business in a separate kind of problem. We're not going to run into meters when we're dealing with molality. What is molality? It's moles of solute, but instead of volume of solution, it's kilograms of solvent, just the solvent. So it's kilograms of solvent, not kilograms of solution. I won't try to trick you on this one, but you may screw up anyway. So just watch out for this one. Okay, so let's calculate a molality. Molality of a sucrose solution containing 50.4 grams of sucrose and 3.332 kilograms of water. So we need to remember what molality is. So molality is moles of solute divided by kilograms of solvent, not solution. So we need the moles of solute, sucrose, and we need kilograms of solvent, water. Well, this problem is making it easy on us. It's giving us the mass of water in kilograms. So we can just write that in, 0.332 kilograms of water. But we need moles of solute. They gave us grams. So we need to do a little conversion. 50.4 grams of sucrose. Sucrose is C12H22O11. And we calculated that molar mass earlier. See if I can find it in my calculator. 342.296. Grams of sucrose per mole. So 50.4 divided by 342.296. So the units are canceling out grams and grams. Okay, caught that. 3 sig figs in our starting number, so this number of moles is going to have 3 sig figs. So there's my 3.147. Write down 2 extras to avoid rounding errors. So that's the moles I need. I'm going to take this, and I'm going to put that in the numerator of my equation. 0.14724 moles. The denominator also has 3 significant figures, and so my final answer is going to have 3. That's without rounding, and then rounding is 0.443, and I can say moles per kilogram, or I can say 0.443 m. Not meters, molality. Any questions? Well, how much does the freezing point get changed? There's an equation for that. Delta, again, is change. Final minus initial is what we usually do for the change. Here, it looks at the change as being a positive number. Again, I wouldn't choose to do that, but that's what everybody does. So the change in the freezing point is equal to the molality times a constant. This is called the freezing point depression constant, very clever name. And that's going to depend on what the solvent is. So if you have water, it has 1 kF. If you're looking at changing the freezing point of ethanol, it has a different freezing point depression constant. And you don't memorize those, you just look them up in the table on an exam, they'll be given to you. So calculate the freezing point of an aqueous 2.6 molal sucrose solution. And here it's giving us the Kf. For water, Kf is 1.86 degrees Celsius times kilograms solvent over moles solute. Even if you forget what the equation is, which it is given on my exam, you can use the units here to figure it out, because 2.6 molal, when we write that by hand, we want to write out what it means, not the abbreviation. That's 2.6 moles of solute per kilogram of solvent. And these units are going to cancel out with the units in that factor. So the equation is the change in the freezing point is equal to the molality times Kf. Well, the molality was given as 2.6, and that's moles of solute per kilogram of solvent, times Kf, which was given to us, 1.86 degrees Celsius, times kilograms solvent, divided by moles of solute. And then when we look at the units, moles of solute cancel and kilograms of solvent cancel, and we're left with a temperature. So we got 2.6 times 1.86. So delta TF, we always want to consider sig figs. 4.8, 2 sig figs in this molality, 3 in the constant, so my answer is going to have 2. Write down 2 extra digits. The unit there is degrees Celsius. Is that the answer? No. That's the change in the freezing point. The question asks us to calculate the freezing point. What temperature is needed for this to freeze? Well, what's the regular freezing point of water? You should know that. 0, right? So the regular freezing point is 0. And does this mean that the temperature goes up or down? Down, because freezing point depression. It causes the freezing point to go down. So we're going down 4.836 degrees Celsius. So that's going to be a negative number. So the freezing point, not the change in the freezing point, the freezing point is negative 4.8 degrees Celsius. Unfortunately, in these, I mentioned it earlier, in these calculations, they do not use the same conventions for delta as being final minus initial, and so it can be confusing. Any questions? For the boiling point, same idea, except that the boiling point goes up instead of down. So the equation, very similar, it's just got B for a subscript instead of F for freezing. And again, different solvents have different values. So let's calculate the boiling point of a 3.5 molal glucose solution. And here we're given the freezing point elevation constant. Freezing point, boiling point. Delta TB, the change in the boiling point, equals the molality times KB. So I'm given 3.5 molal, which is moles per kilogram. And I'm going to multiply by the factor, the constant here, degrees Celsius times kilograms per mole. And those units cancel out. So 3.5 times 0.512. 2 significant figures, 1.792 degrees Celsius. That's the change in the boiling point. What's the normal boiling point? 100. So the normal boiling point for water is 100 degrees Celsius. Is this going to make the boiling point go up or down? It's going to go up. So we're going to add 100 plus this. So we're going to get 101.792. And we would round that to 101.8 degrees Celsius is the boiling point of that solution. There are good reasons that these little topics come in here, because a lot of students taking Chem 3A are headed into healthcare professions such as nursing, and in your nursing courses, you're going to have to deal with some of these things because colligative properties are important in medicine.